think about. These are essential questions to just think about. And we're on slide number 8, just for those following along here. So the essential questions that I'd like you to think about is how can we use a table to determine a limit? What I mean by table is like an XY table and a like input output table. Some of you think of it as a T chart, whatever you like to think of it. But looking at an actual table, how do we use that to determine a limit? Let's say you don't have a graph, you just have a table. You don't want to plot all those points. How would you use a table and try to figure out a limit? The next thing I'd like you to think about is how can we make connections between tables and graphs? Like what connections are there between them when it comes to determining a limit? Those are some two things to think about. Make sure you pause, read this for yourself, think about it a bit before we jump into it. All right. Now we went ahead and at least are thinking a little bit about like, look, that this was the same old problem. I'm bringing this back. And what I have for you here is the two tables. So this was Benny, this is Bertha. This was Bertha's limit motion right here. She was coming in from the left. And this is Benny's limit motion. He was coming in from the right. Remember, they ended up at different y values and they ended up not meeting for their t. And what I have for you here is I went on Desmos and I made a table for Bertha's movement. She started at around the x value of -2, and this was her y value location. She was down here in the negatives. And as she was walking closer and closer to the point of 3, she ended up at the y value of 1, which makes sense right here in the limit notation. So go ahead and take a look at that, and then we'll take a look at Benny's in a second. But just make some connections and also take a look at why I'm kind of like Bertha looks like she's moving faster here, but as I'm coming into 3, I'm getting in really, really close to 3. So we have 2.5. 2.9 is pretty close to 3. 2.99 is even closer to 3. 2.999, even closer. And once I hit 3, we get at 1. Notice how the y is behaving. Just some things to notice right now. And then in your mind, maybe make some connections between what you're seeing here. So that is Bertha's movement. And then we have Benny's, right? So this was Benny's limit. This is his motion, and this is his table. Take a look at his table. So again, he started at around x value of 7, and he started to approach the x value of 3 from the right-hand side. But because he's coming in from the right, that means he's going from 3.5 to 3.1 to 3.001. So I'm just getting really, really close to 3. But then once I hit 3, y'all see this? It's undefined. It's because of that open circle. So if I was to plug in 3 into my function, I would get undefined because the open circle. But even if the point is undefined, I still know that my limit will exist and that Benny will still end up at 5. What connections can we make to what's happening in his table? Notice how I don't really care what's happening here when it comes to limits. I don't care. What I do care is what the function is doing as I get really, really close to 3. The limit is still approaching 5. Notice how these numbers are slowly approaching, actually quickly approaching 5, because 4.9988, that's really close to 5. And this one's even closer to 5, 4.999 infinite nines. The limit is still going to approach to 5 for Benny's case. And we don't really care what's happening at 3. Again, the limit doesn't care what's happening at the point. It matters what's happening really, really close to the point. So that is like huge, huge distinction. Let me go ahead and show you these bullets again to kind of re-emphasize what I just said. So again, when it comes to limits, it doesn't matter what happens at the point, such as when you have an undefined value. But what really happens close to the point, Benny is still approaching the y value of 5, even if the point itself is undefined. So that's important. because our functions can have undefined points or even asymptotes, it's important that when we investigate limits using a table, we make sure that our tables are getting really, really close, or you could use infinitely close to the x value of the limit. So that's why I'm doing this. That's why these points starting to get really, really close to 3, because I'm trying to investigate what's happening around 3, not at 3. Likewise over here, I was getting really, really, I think I did a better job on this table. I took my time getting really, really close to 3, noticing that the limit was still indeed approaching 1. I actually didn't even have to look at this to make the prediction that this was going to be 1. The y value is approaching 1. So yeah, definitely. So this one's huge. Take your time. This is something that we're going to continue to work on, making connections with limits and tables. And it's going to be the thing that we'll be doing some group work on. So first, let this sink in. And then we're going to have a Padlet check-in a second. Let's see if anyone has questions on this part. And make sure you read the little bullet points there at the bottom. It's kind of synthesizing what was just said. And again, continue to make connections with what you see in the graph and what you see in the table. What do you see in the limit expression? How do they kind of match up? For credit. And again, that's true. So, right, if we look at the graph at 3 in the table, it's undefined, and that corresponds to the fact that there's an open circle, but the limit still exists there, and it's going to be at 5. Awesome. And then, okay, we have that someone thinks it's easier to find the limit notation than the table. So the table looks a little bit complex. You could determine the limit and determine if it exists if the table from both sides are the same for the y side. That is deep. Yeah, we might get into that actually in our next class meeting. Yay, we're already kind of thinking ahead there. Awesome. The limit notation is represented clearly in a graph. So for this particular, so some of you are able to see it more clearly in a graph. And both the graph and the table connect because they both have the same numbers. Yeah, you can make the direct connections. But the table shows the exact steps it took to get the final results. And you could use a table to determine if a limit exists by looking at the x and y values from both tables, right? Ooh, the table gives you a more precise number than the graph. And it says in the table, in the graph, you could see it clearly, and in the table, it jumps by the y values. Yeah, I see 2 of you mention the jumping part, so that's interesting. And then you could see the limit on the graph and if it exists for the table. And then the table looks complex. Don't worry, we're going to get some instruction on how to actually make these tables. So it shouldn't be too scary, I'm hoping. All right, y'all. We're going to go ahead and spend this next portion taking a look at these steps. So we are all on slide number 11, y'all. So again, you can be on your own copy. So these are the steps that I'm talking about. These are adapted from Khan Academy, by the way. Let's go ahead and take these 4 minutes. And then after the 4 minutes, I'm going to take us into our checkout. But let's take these are all super good questions. I can't wait to, we'll open up class answering this. Yeah, attendance in this class is really great. Cool. So it looks like we're just missing Denise and Carlos. Ball is being thrown and it has kind of like this projectile motion in the air, like boom, it's thrown and it's moving along like so. Another thing I want to point out is in this graph, the time is in seconds. Down here you see seconds. And then the height of the ball, let's say it's meters. It's labeled right here. And I want you to think about this question. Imagine you have a ball and you want to figure out how fast it's going. What can we do? If we have a graph that looks like that, how can we determine the speed or the velocity of the ball. So we got right here, we got d over t, and I'm assuming we're thinking distance over time, that formula, okay? So we got s, or speed, equals distance over time. We have v, or velocity, distance over time with a question mark. So a lot of you are agreeing on this distance over time. Ooh, we have a new thing here. So we have something like v1 minus v2 over sec. I forgot how the equation goes. Ooh, bringing in some physics knowledge. That's awesome. Ooh, okay, we got to find the slope growth for the distance of 1 sec for the specific time you want. And since the speed changes every second, we probably average out our graph to get an even speed. Wow, so that's an interesting, okay, interesting thought process there. And then we have another one where this v1 minus v2 over time of sec. So that's like a physics thing that was mentioned. And then you calculate the distance and time and ticket to get speed. I agree. I love it. So far, everything y'all are saying on point. The ball is moving at a speed of 3. Oh, okay. A calculation, 3 meters per second, because the ball is at 9 meters at 1, 6 and 2 in the slope. Okay, we're seeing a slope. We're seeing mentioning of physics. We're seeing distance over time. All right. A lot of know exactly after 2 seconds how fast you're going at that point in time, not an average. What will we do then? This is now ideas being thrown out, y'all. So we definitely want to value the time you are taking to think about this first. Before I'm like, hey, this is how we do it. Let's think about it. All right, let's see what y'all said. So we have some inferences that you can count how many points are on the line between 1, comma 9 and 2, comma 6. So kind of like partitioning it somehow, narrowing it down a bit. If I remember, you can use slope to help you find the speed of car at 2 seconds. Okay, so thinking that slope is still going to be involved. Awesome. Then we have, what if you just do 2 divided by 2 seconds? That's an idea. You can find the slope / create a small slope near the exact point at x equals 2. Interesting. Using a smaller slope is. You can see what the point of the ball is going, and base it off the slope, you can see the speed. Okay, so using your graph there to kind of make an estimate. Then we have, you could do 6 divided by 2, which is 3 meters per second squared. Yeah, which is very similar to what we did before, right? In that slide 6, I believe. And then maybe plugging into an equation, maybe using a table. I like those ideas. Wow, those are really, really good. I think we could look at the number it started on and the end number and see how long it took between there to get to the end. Wow, this is so great. Wow, these are awesome. Maybe when you find the slope near the point of x equals 2. So another mention of that, I know someone else mentioned that too. You can call something. It's a long word, instantaneous rate of change. So remember the thing we just did before, that's called average rate of change. This is called instantaneous rate of change. Now, I'd like you to think about this. The best relation I can make this to is when you're looking at the speedometer on a car. Like either your parents, or if you drive, right? If you have your permit, or sorry, not permit, if you have your driver's license and you're driving, whatever. But everyone's familiar with this speedometer, right? So when you're driving a car, the speed you see on the speedometer, do you all think this is an instant, or is it an average speed? Is it telling you how fast you're going at that moment? Or is it telling you on an average how fast you're going? For this one, go ahead and use the chat. We're not going to use Padlet. So use the chat here to answer this here question if you're ready to. If you're not, just think about it. What do you think is happening here? And let's see what we get. All right, we have 2 that say average there. And then, so 3 who are saying they think it's like an average. We have someone saying instant question mark. And then remember, average would mean that it's telling you after every so minutes or something, like how fast you're going over a certain amount of minutes. So we have average and instant. Okay. Let's see if there's any other ideas, or if anyone wants to add a because or anything like that. I just want to give everyone time to think about this, and then we'll see what the answer is here. Okay. Oh, okay. Bye, Rob. Rob. Okay. So let's talk about it. So let me give you the answer. So The speed that you see on the speedometer is actually your instant speed, everyone. So I know a lot of you said average. It would be an average if it was like perhaps telling you after 1 minute or so, like, oh, this is your speed between the first minute you were driving. This is the speed the second minute you were driving. But don't you notice, y'all, like when you're driving, that speedometer, that thing, that red thing is constantly moving. It's adjusting like how fast you're going in that moment, actually. So this is actually called an instant speed. So think about that. Think about how fast that I wouldn't know what that red thing is called. It's like that. If someone thinks of a word, let me know. But that is constantly moving. So within a minute, right? I could do a variety of speeds. Within a minute, I could speed at 100 miles per hour, and then I could slow down 5 miles per hour, speed up, slow down. I could do a lot of things within 1 minute, and my instant speed would be very different throughout that time. So the speedometer is telling us an instant speed. Um, so then what does this relate, right? So overall, the instantaneous rate of first off, the instant rate of change or the instantaneous rate of change, they mean the same thing, is when you determine the rate of change at an exact instance. So that speedometer thing in your car, that's an instant rate of change. And that's when we're trying to determine our speed or velocity, whatever, at an exact point in time, at that instance. So that's an important definition of what an instant rate of change is. Next one is, well, how do we do this? You all put a bunch of different ideas right now on the Padlet. This is the process that we're going to be doing. This is the process in the big ideas packet. Some of you did mention this process about making the slope smaller, but we're not making the slope smaller. We're going to be estimating the instant rate of change by moving one point closer to what we call the point of interest, or whatever point we're interested in. And the last problem we're interested in at 2 seconds. So you're going to see visually what I mean by this once we do this, but this is the process. We're going to move one point closer to the other point, and then you're going to calculate the slope of those two very close points to get an estimate of your instant rate of change. And maybe, I don't know if choosing 2 points that are very, very close together, I wonder if that reminds anyone of a past big idea. I know it's been more than a week, but feel free to share if it does remind you of anything in the chat or not. It's okay. I'll just give some time, or think about if this reminds you of anything. When we're making points really, really close, I wonder if that reminds someone of a past big idea. Oh, let's see. I forgot its name though. It's the getting closer thing. So Danny, you're right. It is the getting closer thing. I wonder if anyone remembers the name. But you're right. It is the getting closer thing. We have a formal name for it. Starts with an L. Maybe
Limits?
yeah, think of the Mean Girls movie. Remember the limit does not exist. Well, in this case, the limit will exist. But yeah, the thing about like making 2 points or anything get closer and closer or approach something, that's limits. So this is actually us. We're going to be applying that big idea of limits. So I put it down here too. The process of moving 2 points closer and closer together, that is us applying our big idea of limits, everyone. So that's actually why this is even at all related to what we were doing before we hit the break. So we're continuing that. See how it's all kind of interrelated. So it shouldn't just be me teaching you random stuff. It all has a storyline that is leading up to something. So yeah, just think about that. This is just important to read and be prepared for what we're going to do next. So our goal now, we're still going to be looking at that ball problem again, but this time we're going to try to find the instant speed at 2 seconds. How fast is it going exactly at that time? And again, we're going to be doing the process of the second bullet point. We're going to estimate it by moving that other point closer to it. Let's do it. All right, y'all. Example 2. And I went ahead and we're on slide, I don't know what slide this, slide 10. We're on slide 10, everyone, example 2. Here is the strategy up here. We're trying to figure out how fast the ball is going at exactly 2 seconds. So we're moving that green point. Remember the green point? It was at 1,9. we're moving it now closer to 2, very close to 2. Take a look at my picture. I just basically went on Desmos and I moved that green point very close to 2. Instead of x being 1 seconds, I made it 1.9. Notice how 1.9 is very close to 2? That's why I chose that point. So now I have 2 very close points, and we're going to go ahead and try to find the slope of this. The slope of that is going to give me a better estimate of the instant rate of change at exactly 2 seconds. So let's do it. Step 1 is I'm going to, because I know I'm going to be using the slope formula, I'm going to start to label it. So I'm going to do x1, y1. And then we got x2, y2. And we're going to just go and do our handy dandy slope formula. Here it is, y2 minus y1 all over x2 minus x1. We just got to plug in and subtract. So according to these new coordinates, I'm going to do 6 minus 6.75 on top divided by 2 minus 1.9. You're going to need a calculator. I definitely did. I used my phone. So this is what I got when I subtracted the top numbers, and then the bottom I got 0.1. I went ahead and divided these two numbers to see what we get. And I got that my slope or my speed or my velocity here was negative 7.5 meters per second. So remember previously what we got, I think negative 3. Now we got negative 7.5 when I moved the points closer. So right now we're getting a better estimate of how fast we're actually going at x equals 2 seconds. Notice that we're going faster than between 1 and 2 seconds. So think about that. So that's what we got so far. Oops. And let's see, does anyone have any questions of what we just did here? I'm going to pause and make sure you have your questions addressed. You could ask me privately or openly, whichever way. All right. So, okay, cool. We got a pretty good estimate here, but guess what? We could do even better. What if I question for you back on the Padlet? And let me get you the Padlet once again in case. I'll give you all a minute there. Again, don't forget to put your name or initial. Again, any thought or any contribution on the Padlet is completely valid. And then we'll talk about what we see. All right, y'all. I'm interested to see what y'all are thinking. So, as the 2 points are moving closer and closer, first pay attention to what we're doing. We're moving these 2 points closer and closer because we're trying to find the instant rate of change, or another way to say that is how fast the ball is going at exactly 2 seconds. So, in this diagram or in this picture, screenshots of the different calculations we did, we first started out calculating the speed between 1 and 2 seconds, and we got -3 meters per second. Then I moved this green point even closer to the 2,6 point, and I got an even better estimate because, again, the closer the points, the more close you're to determining the instant speed or the instantaneous speed. Then I went even closer, and then we got a slope of -7.9 meters per second. Again, that's going to be velocity. And I asked you, like, how is that secant line, that red line, changing? And as well as how in the world is this at all related to limits? Let's think about what y'all said. So we have, as the 2 points are getting closer and closer, the secant line takes a closer angle to that of the graph. So it's kind of like, I guess I could see like it's more angled, like it gets more angled. I could see that happening. When the 2 points get closer and closer, the secant line starts to move closer to the actual slope of the graph. Wow, that's really cool. Yeah, that is actually very powerful. I love that one. That is exactly what we're doing. So as the 2 points are getting closer and closer, the line is almost like becoming the exact slope of what's happening near that area of the graph. That is amazing. I love that one. Yes. When the 2 points get closer together, the slope of the line seems more similar to the actual slope of the graph. Yeah, that's similar to what was said prior. That, yeah, I think these two are saying the similar things. Amazing. The line is getting steeper. Yeah, that was mentioned. So I agree. So over time, as the points are moving closer and closer, the line is indeed getting steeper, right? I see that too. All right, the line gets steeper and steeper, and the 2 points get closer, and it looks more like the graph. Yes, that is, y'all are hitting the main points. Y'all are seeing the main essence of what's happening here. And then, yeah, so another way to say the line getting more steeper, I like this wording, the line gets more and more vertical, meaning the points are getting closer and closer together. That's another way to think of it, the 2 points or the line getting steeper. Ooh, okay. So this is an attempt to bring in limits, which I love. 2 points move closer to the points, going further down, making them have a limit that is a similar distance. We have it becomes vertical. We got more vertical mentions. And then we have that the secant line becomes more direct to the slope, and the line is decreasing as the slope is getting smaller. Yes. Y'all, this is really, really great. Again, this is what we're going to be doing to answer part of our mini final once we hit there. I think I already posted it though, so y'all are free to take a look at it, but we're not going to talk about it yet until we hit there. So we'll get to that. All right, y'all. So let's see. We're not going to be doing the checkout form. So we're going to have, so this makes it so it's not an average change. So when you're doing an average change, you're like finding different intervals, like, oh, between 1 and 2 minutes. And then you're gonna have to plug it into that slope formula, and then you calculate. So this is actually an instant rate of change. Not only that, but we talked about yesterday how we can approximate the instant rate of change. So what I'd like us to do is I'm going to go ahead and put this Padlet here into the chat so you could review, but I'm going to open it up with you. So we're not going to answer anything yet on there. This is just for you to open up and to review what we did yesterday. So again, this is me recapping right now on what we did. And again, this is our running Padlet. So you could totally take a look at all the like reflective questions you answered and your thoughts. But I'm going to go ahead and take us to yesterday's. So first I asked you all, what can we do to figure out how fast a ball is going if we're given its like motion and its graph like this, where its height is in meters, time is in seconds, if you see the labelings right here, right? And then a lot of you mentioned slope. A lot of you mentioned some physics formula. A lot of you mentioned distance over time. That was the most mentioned. And all of those were correct. The key idea here is yes, we're using slope, we're using distance over time. Those are synonymous to find the speed or velocity of a moving object. The next thing is we talked about how we can approximate the instant rate of change. So our goal was we tried to find how fast this ball, because this was a ball being thrown, how fast the ball was going at exactly 2 seconds. So in this last picture right here, you notice how this second point got moved closer to that first point that we were interested in. So this green point got moved closer, closer, and then even closer. And from there, this last photo would give us the best approximation for the instant rate of change at exactly 2 seconds. In this case, it would be negative 7.9 meters per second. So not forgetting your units, I just couldn't fit it here. And I think one of you said you would say it would be around negative 8 meters per second if you were to continue that trend of moving the point even closer to this 2,6. So that's what we did yesterday. And you all can go ahead and reflect on what you all said here when you rephrased your understanding. Again, many of these were really good. And you also were taking a look at how the secant line, so I forgot to mention that, but the secant line was changing over time. So a lot of you mentioned that this secant line was basically kind of like becoming the slope of the graph. I really like the word that some of you used. And that's exactly what's happening. We're kind of finding exactly what that slope is at that point, and that's why it gives us an instant rate of change. So that's just, recap, and y'all can go ahead and look back at what you all thought, what you said, that line that was getting steeper. The link didn't work. Okay, so now we're going to go ahead and talk about this. So I kept talking about how in order to estimate change, all you got to do is to move the points closer to each other. A question has arisen, whereas why can't we just put the 2 points right on top of each other? For example, why don't we just have 2,6, 2,6, like they're just right on top of each other, and then we find the slope, and won't that tell us the instant rate of change? Or won't that tell us exactly how fast that ball was going after 2 seconds? Let's investigate what happens if we do this. So if we do this, first off, we know we need the slope formula to find either speed or velocity. And we know that we need a y1, y2, x1, x2. But because we only have 1 point, right? I put the points right on top of each other, like in this visual, there's no 2 points. That means this point has to be both x1, y1, and it also has to be x2, y2. It has to be both of them then. I mean, what other choice do we have if we only have 1 point? So wouldn't this give us the exact instant rate of change instead of just estimate? Well, let's see. Let's go ahead and plug it in. So y2 minus y1, that's just going to be 6 minus 6 on top. And then because x2 and x1 are the same number, you're going to get 2 minus 2 in your denominator position. What you end up getting is 0 divided by 0, right? Now, I mean, I would like you all to try and see what you get on your phone, or if you're using Google, whatever, as a calculator. What do you get when you do 0 divided by 0? Let me know in the chat. If you get something similar or different to what I'm getting, what do you get when you do 0 divided by 0? All right, so Daniel says error. Did anyone get anything different? I went ahead and did it on my phone. This is what my phone told me as well. So similar to what Daniel got, error. Gerardo also got the same thing. If you were in my class and we were using the calculators that are in there, man, I hope they're still in there. I like those up. But anyways, if you were in my class, I think the calculator would give you something like error, and then it would say div by 0 or something like that. Basically, it's saying division by 0. Yeah, so we're getting an error here, and there's a reason for that, why this ends up not working. We can't actually divide by 0. That's actually a mathematical fact. There's like a lot of YouTube videos on that, by the way. Like, if you're interested, you could take a look, but you can't divide by 0. That's when the 0 is in your denominator position. You can't have that. You're always going to get an error. You can literally test this out on your phone or anything. Again, it's a nice thing to investigate. Hey, maybe some extra credit opportunity to type up some investigation on that. Hey, if you're interested. But yeah, you can't divide by 0. And for this reason is why we can't just put the 2 points on top of each other. So we have to actually just move the points infinitely closer to get a best estimate. That's what we're going to be doing when we're trying to find the instant rate of change. So that's the why we can't do this, because we're going to get an error. So that's super, important to think about. Let me know if anyone has questions right here about this portion. All right, awesome. No questions? Let us move on then. Thanks so much for your engagement, those who checked in their calculator to see what you got. But yeah, that's why we can't do that. So now, y'all, we're going to go into the part that you've probably seen in the textbook, and it's important for you to have the exposure to this. And let me also prep you all. We're gonna have a Google form that's gonna come up right after I finish these like last 2 slides. We're gonna have a Google form. You want to pay attention, so just heads up, because I definitely want to see what you're understanding, what you're not, all of that. It's not about being right. It's about sharing your thinking with me. Is what I'm really concerned about. All right, so we're going to try to kind of formalize this. So we're going to rename our coordinate points. And what I mean by formalize is I'm trying to generalize this for any 2 points, not just 1,9, not just 2,6, for any points on any function. So I'm just going to rename my points. This one, this green point, I'm going to call x comma f of x. It's like x comma y. F of x is just a formal way to write y. It's a function. So that's that. I renamed that first one. So if this is x comma f of x, what in the world would this be? Now, this point right here is shifted by like a horizontal unit that I don't know what it is. Let's call that horizontal unit. See this arrow down here? Let's call that h. Let's say it moved h units to the right. Yeah, to the right. If that's the case, then we can rename the second point to be this. X plus h, because it moved over, plus h, comma, f of x plus h, because that's the thing you're going to plug in to get your y. Let's see that. Let's see, does anyone have questions about this? So right now, all I did is I renamed them to just make this applicable to any 2 points for any function, because we're going to create a formula right now. So let's see if anyone has questions. All right, let's see. There's something in the chat. What does H represent? Yay, thank you for asking that question. H represents the horizontal distance that the second point is away from the first point. It's a good question. Let me type that out too, the answer to the question. H represents the horizontal, like side to side, horizontal distance. The second point is from the first point. And then we have, why do you add H? So we add H because we have 2 separate points. The first point is pretty straightforward, like, hey, let's call the first point x comma f of x. So if I need to define the second point and I need to make it related to how I define the first one, that's why I'm adding H. So I could define a second point. So that was a question. So why am I adding H? We are adding H to define the second point. Second point, in a general way is my best way to kind of say general function notation format. And let me move this up. Let me move it right here. Here's some answers to some questions there. Again, so first question was, what does H represent? H represents the horizontal distance, and it's down here if you see this arrow. The horizontal distance at the blue point is away from the green point. And then another question was like, well, why are we even adding H? We're adding H because first off, we define the first point as x comma f of x. To define the second point that's related to how we define the first one, we needed to add H. So, and then here's my answer. In order to define that second point, we needed to kind of include this horizontal distance away from the first point. These are really great questions. Any other questions so far about how I renamed these points? I love those questions. It was awesome. This is actually, so just so you know, this is touching into calculus. We're in pre-calculus right now, but this is touching into the theorems that arise in calculus. All right. All right, y'all. So according to finding the speed or velocity, we know that we need to just plug into a slope formula. Remember, y'all? So that's just the thing we've been doing recently, right? Oops. Let me not pop that up yet. So that one looks scary, but let me first do the things. Okay, so imagine I want to find the speed of whatever this thing that's moving between these 2 points. Well, we know that all we got to do is first off label our points. So we're going to do x1, y1. And this one's going to be x2, y2. So we're going to try to create like a general formula for the speed using 2 points. So then we know that we're going to plug into the formula y2 minus y1 all over x2 minus x1. And we're going to go ahead and just plug in these values. So it's going to be y2, so this thing, minus y1 all over this thing over x. And that's where this funky looking formula is coming from. You see that? See how it's y2 minus y1, then you have x2 minus x1. So y1, y2 right here. We got minus y1. Then we got this part was x2. And then we have minus x1. Now, let's see, does anyone have questions about this funky looking expression? Because all we did is this is actually representing the slope of 2 points. We're trying to connect the slope with speed and or velocity. Let's see if there's questions.
So wouldn't it just equal h over h?
Wouldn't it just equal h over h? That was a good question. So basically, I think I see what you did here. You did like f of x minus f of x, right? On the top to get h. And then at the bottom, you did x minus x. Is that correct?
Yeah.
Okay. So the bottom part, you're right on. You're spot on. Now the top part, here's the problem. We can't just take the f of x out. This is kind of like stuck. You can't just, you can't say, okay, f of x, and then you're left over with h. This has to be stuck. We can't just pull out the inputs of this expression, if that makes sense. It's kind of stuck. This right here, we can't change. So it's not going to become like f of x, and then you have plus h. Good question, though. Good, and I like how you already simplified the bottom. I'm going to show you all what this simplifies to, though, in a second. Any other questions, though, about the setup in general? All right. Let me just, let me erase some of this just because it's going to get in the way of what I did. But just so you know, all we're doing is a slope formula after we renamed our points. Now let's simplify. Now, again, we already talked, I kind of verbally kind of explained why we can't just take the f of x out of here. There's no algebraic way we can do that. This has to stay. But y'all, let's look at the bottom here. The bottom here is kind of free. There's no f of whatever trapping any variables or inputs. What is something we could cancel out here? And I know Danny already kind of told us what you got, but what cancels out here only in the denominator position? We're just looking down here. What's something that cancels out or goes away? So let's see. Yeah, Yes, I have three people in direct message who are all saying X. You are all correct. Yeah, y'all can see that. Let me just show you. So X minus X, that is something you can cancel out because X minus X is simply 0. Again, we can't do anything with the top, but let's go ahead and show you what that looks like. This funky looking expression simplifies to, boom. This is the general average rate of change formula, everybody. It's just a general one you would see in a college textbooks. But all it is, y'all, all it is your slope formula. That's all it is. Like if you see it, don't get afraid. This is literally synonymous to that, just written in a general way for any 2 points. But that's all it is. And again, let me write this out. This is the average rate of change formula, aka slope. And then write one more slide, and then we're going to have our Google form. Again, it's very great how I'm seeing a lot of questions coming up, a lot of interaction with what's going on here. Let's see, is there any questions about this last part? So this is all on this side, and then we're going to do the next slide. All right, let's see, there's something in the chat. And then Alexander said, oh, sorry. Sorry, is that the answer? That's the answer for this slide. So that right here is what we were trying to come up with, is just the average rate of change formula. That is the answer. For this slide. So this is the average rate of change formula. In the next slide, I'm going to show you how we're going to look at what is the instant rate of change formula, right? So we're using the average rate of change formula to define the instant. Remember, average means it's like 2 points that are far apart. You're trying to find, like, on average, how fast am I going? We don't want to care about on average. We want to find out at this instant, how fast am I going? That's when we're going to be using limits, and or that's when we're moving the 2 points closer and closer together, like we did on the we saw on the Padlet when we reviewed. All right, let me go ahead and clear the screen. If there's no more questions, unless there's a burning question. Again, this is on Google Forms, so it's good to ask your questions. We got one more slide, and then we're going to do Google Form. And after that, we're going to do one last activity. All right, friends. Let me go ahead and let's go to the next slide. And I'm sorry that it's all just here, but here we go. This is the instant rate of change formula, aka definition. This is it. So notice how the formula basically has the average rate of change formula. This is the average rate of change formula, the one that we just constructed. This is simply the average rate of change formula. Except it has a limit in front of it. Notice how the limit is saying as h goes to 0. This h going to 0 means the horizontal distance is becoming 0, or basically the distance between the points is going away. This limit is basically representing the 2 points moving closer and closer together. That's what we were doing on the Padlet yesterday, and we were investigating how to estimate the instant rate of change. This is it. This is the definition. And on your Google form, I believe I'm going to ask you to interpret some parts of these. So again, I call this first one the point of interest y value. That point that's not moving, it's just your second y value point. This one's just, or whatever. So point of interest y value, the one that's not moving, and the other y value, and I called this one the second one. This h, remember, that was the horizontal distance between the 2 points, and the limit right here represents the 2 points getting closer and closer together. So this formula has a lot of information. This class, you won't be asked to calculate using this formula. What you will be asked to do in your mini final is to estimate instantaneous rate of change, which we could do because we know that concept of moving 2 points closer to each other. That's what you're going to be doing in our mini final. Also, last thing, this instant rate of change formula in calculus has a specific name. It's called the derivative. I don't know if you've seen that word, or maybe you know people who are in AP calculus right now who have heard that word so many times, they're probably tired of it. But this is the formal definition of instantaneous rate of change. And that's synonymous to the derivative. Again, this is in your big ideas packet. So maybe some of you, when you annotated that, got a little freaked out when you saw this formula. All right, now I'm gonna pause for questions about this slide. So this is for instant rate of change. Let's see if there's questions. And if not, then for those of you who are ready, you could just go to the next slide on your slides and you could start the Google form if you're ready. But everyone else, I'm just pausing here to see if we have any questions about this, because you're going to be asked a question about the formula or where something came from in this formula. All right. Do you think we're ready? Ready for that Google form? Okay, Google form will be for credit, y'all. Please make sure you do it. If I am missing a Google form, I'm going to send an email. I just sent an auto email for those who are speed for these at the bottom. Let me know if anyone has questions about this, just overview of the essential questions. Again, I know I've been always bringing this back, but it's super key. Okay, awesome. So I'm going to go.
Question number 8. We don't know how to do it.
So which one? We don't know how to do it?
Yeah, we need help.
Okay, what can you brief me on where you all are at? What did you try?
This one. What is the fastest speed that the car actually reached during its drive? You can go back to slide 4 as you try to determine this. Refer to your model and use your model to show us your evidence.
Wait, I got a question for you, Mr. Dano, that I think can also like answer this. Is this like the thing where we gotta draw the lines for each, like, since this is like a little squiggly line, do we just like draw a line on each squiggly line and see which one's the steepest? Is that what it's asking to do?
That sounds like an idea, Danny. I mean, that sounds good. Were you saying secant line? Or were you saying
what?
Were you saying secant or squiggly line? I wasn't.
Oh no, I said squiggly because it has like little, like you could draw the secant line on the squiggly. So when it goes up.
Okay, I'm not able to. I don't know what. Yeah, it's hard for me to envision that, but I think that sounds right. You're saying draw these lines and see which one's the steepest. I think that sounds like a plan, right? Because the steeper the slope, the faster the what?
The faster the speed.
Yeah.
I mean, well, yeah.
Okay, so let's go back to that Desmos thing y'all were looking at for this group.
So we can screenshot this and then show this in answer 2.
Yeah, you can.
If it's right.
It. Yeah, you could, if it's right, screenshot it, and then your job will be to justify it.
Okay.
Justify what is the speed. So let's try to apply your idea. So what would you recommend they do? So in this tool, by the way, who's sharing? Is this it's Yaisa? So you're able to move that purple line. So like Yaisa, can you show us how that line moves? Oh, okay, you could use this little bar there to kind of move it around. And we're concerned about the first 9 minutes, right? So we want to see the full 9 minutes of the teacher's drive. Question: would the slope have to be less steep, more steep, no steep? What do y'all think? If we want fast speed.
It could have to be steeper because you're traveling the farthest distance in the least amount of time.
That's right. So we want to find or locate an area or a segment in these 9 minutes that would, and that looks very steep. I see this, the point.
Yeah, right there.
That looks pretty good. Maybe we could zoom in around there and see at around, oh, and also if you look at the sidebar, it tells you 3.23. It's saying that X is 3.23. Or you could click on there and see what that coordinate would be. Okay, so that's a coordinate. All right, so in this group, first off, just making sure, like, does everyone see like why we kind of stopped there? And or if anyone has questions.
Looks like it's the steepest you're gonna get.
Okay, looks steep. Okay, now, if you were to try to figure out, and this is for your group to try to figure out this next, so definitely take a screenshot of this, and or maybe someone should write down that number. But your next step, I'm going to be popping into other groups, so I do want y'all to just struggle with this a bit. But now, what are we looking for? Are we looking for an average or instant rate of change? Is my first question.
Instant.
Okay, instant. So like an exact point in time where they might have been speeding. That's a good answer. Now then, what else do we need? We have 1 point. What else do we need to find the instant rate of change? And that would probably be a question for you all. So try to figure that out. So yes, we're going to be finding an instant rate of change. We've identified an area where the slope looks the steepest, but then now what? What else do we need to calculate or estimate their instant rate of change? And then AJ put another coordinate. He put 0, 0. Y'all can go ahead and discuss this. I'm gonna jump into the next group.
Wait, you're on your phone?
Yeah, I'm
Maybe,
on phone.
Daniel.
That's
Maybe
why I'm
if
not
you just weren't on your
screen sharing.
phone.
I'm a screenshot. Also, the screenshots are so much better on phone too. So
Oh shoot, well, I don't like that.
can you like move it like so that like we can see this? Diego, it's not funny. You know, I'll just screenshot it. It's whatever, I guess.
Eddie coming in clutch with the screenshots.
You know what? No. I need to see the numbers. That's why I can't see the X value numbers.
You could have sung it before, Danny.
Okay, thank you. That's kind of what I was asking to like scroll. I don't know the directions to describe it. All I know is like I do it with my phone and I can't describe it, I guess.
So this would have been so easier if we were in person, if Rona wasn't a thing.
Right. It really would have. Really would have. Okay.
We have 10
Now
more tech issues on here than we would have if we had it in person.
now go to 0.5. Now go to 0.5. You
Okay,
don't know before you do that, zoom into that. Zoom into it. Might as well just zoom into it.
It's weird that I have like
Daniel.
There you go. That's good. No, that was it.
What are you looking for, Danny?
Back. More accurate-ish photos. More
That
back,
was
please.
an accurate photo. I don't know what.
Zoom out a little more, please. Well, not a little bit, like a lot more. Like to show like 1 through 5. There you go.
Or a group could share. I think both groups, actually it was one of the groups I was in today that was like identifying how we could find or kind of narrow down where the teachers were speeding. Let me just give an opportunity if anyone wants to kind of put that in the chat, but like, what can we do with this tool to figure out where in the 9 minutes of the teacher's drive, right, would they have been going the fastest? And thus we could figure out whether or not any point in their drive, if they were speeding. So let's see if anyone has any, like, how could we use this tool to do that? If you want to share with what you did in your group. Let me give you some time and then we'll be great. So how can this tool help us before everyone leaves?
Okay, so what I thought from like your previous, like from earlier today when you like showed us the example of like just drawing the lines and comparing them, Well, you can move this purple tool, and then I guess you can screenshot some of the places and then compare your screenshots and check which of the lines look steeper at which points. And the steeper the line looks,